Okay guys, now we're going to take a few notes about electrons and light. Okay, a lot of this you will see in real life when we do our glow-in-the-dark pickle demo, and on Thursday we will also be doing the flame test lab. So we'll be making flames turn different colors, just like this picture here. So let's make sure that we have our notes out. Okay, it's the next part right beside the isotopes worksheet. So the first thing is the electromagnetic spectrum. Okay, you learned about this in physical science, but electromagnetic radiation, which is the first blank in your notes, is a form of energy that exhibits wave-like behavior as it travels through space. And you've probably seen this spectrum before, but you have visible light in this tiny little area, so red, orange, yellow, green, blue, indigo, violet. Okay, we have radio waves, both AM and FM, microwaves, infrared or IR waves, ultraviolet. Okay, ultraviolet waves are the waves that sunscreen protects against, that you can damage your skin. We have X-rays, which we know can go through bone and things like that, so you can get pictures and images of inside your body. And gamma rays. Gamma rays are the things that you kind of see on the movie The Hulk that turn the guy into like the big green monster. So not super great. But our visible spectrum is this tiny piece of an actual larger spectrum. And you'll notice that energy gets higher as you move through the electromagnetic spectrum. So down here you have a really long wavelength, and if you have a long wavelength, that's a short amount of energy, small amount of energy. If you have a tiny wavelength, right, 10 to the negative 14, then you have a lot of energy. But we will talk more about that later. First, we said that this is something that exhibits wave-like behavior. But what is a wave? Let's talk about it. So you have an image similar to this on your notes, and you need to label them. So A is your crest. Okay, the crest is the highest point on the wave. So you can see how the wave goes up, reaches this point. Each point along the top is a crest. The trough is the lowest point on the wave. This red line that cuts it through the middle, that's the point of rest, where it's kind of neutral. It's back at its central ground. The amplitude is the distance from the point of rest to the crest or trough. And the wavelength measures the amount of energy, right? If we have a large wavelength, we have a low amount of energy. If we have a small wavelength, we have a high energy. And it's the distance from trough to trough or crest to crest, depending on where you are measuring. But always know the closer your wavelengths are together, the higher the energy. So you should be able to use this information to fill in parts 2, 3, 4, 5, and 6. Okay? 2 through 6 should be able to you should be able to fill in based on what is on this slide. So I'll give you a few moments to do that. Okay, if you haven't gotten it yet, you need to hurry up. The sub can also pause the video if he feels like y'all are taking a while, but we need to move through this so that you have enough time to do all of your work. Okay? So, the next thing after we talk about waves is visible light. Okay? Visible light, which is number 9, we will come back to numbers 7 and 8 in the next slide, but number 9 is about visible light. Okay, we said it's that small portion, and it goes in red, orange, yellow, green, blue, indigo, violet. Roy G. Biv is the way I remember it, and you need to write down your colors of the rainbow in order of increasing energy. So we have low energy, which is red, has a long wavelength. This symbol right here stands for wavelength. So violet has the highest energy because it has a very short wavelength. So you need to know that this is the symbol for wavelength. It will come back up in just a moment. And you can see this is the Pink Floyd album, but when you have normal light that goes into a prism, looks kind of like a triangle. The glass will break it into its individual colors based on its wavelength. Okay, so white is a combination of all visible colors, and black is actually the absence of any colors. So let's go back to 7 and 8. Okay, so light behaves as a wave. This is what we mentioned. So wavelength, which has the symbol of the Greek lowercase letter lambda, that's this little upside down Y symbol, is the distance between equivalent points on a wave, and we measure it in meters. Okay, frequency, which has a symbol of F, or this V right here, the Greek letter nu, is also frequency. So that's actually a mistake on my PowerPoint. It shouldn't have an F. It should have this lambda. So you can change that on your notes. But all electromagnetic waves, including visible light, travel at the same speed of 3.00 times 10 to the 8th meters per second. Now, to keep that in mind, this is several football fields. Okay? One football field is 100 feet, right? 100 feet, 100 meters, 100 feet. So this is about 30 football fields lined up, and one thing of light travels that long in 1 second. It's extremely fast, okay? The frequency, right, is the number of waves per second. So it's counting how many complete waves pass in 1 second, which can be very high or very low depending on how long your wavelength is. It's measured in hertz, which is symbolized as an Hz, or 1 over s, which is seconds. Okay? Hertz and 1 over seconds are the same thing, but this guy Hertz, he did something cool, so like, hey, we'll rename this unit after you, which is kind of dumb, but it's what they did. So, in a vacuum, what's really cool is that a vacuum, all matter travels at the speed of light, which is why if you were to get put in a vacuum, you would die, because your body is not designed to move that quickly. So right now, in our classroom, visible light is traveling this fast. The light from the ceiling to your eyes is traveling this quickly, which is why it never looks like anything is changing. You can't see the individual waves because it's moving too quickly for you. So you need to think about problems 10 and 11, problems 10, the frequency and energy, how they're direct, okay? You can look at that when you talk about, right here, okay? So, relationship between energy, wavelength, and frequency, okay? Energy is inversely related to wavelength and directly related to frequency. What that means is if I have a high frequency, okay, if this is how many waves pass in a single second, then I have high frequency. I have 1, 2, 1, 1, 2, 3, 4, 5, 6 and a half waves, whereas this has 1, 2, 3 and a half waves. So high frequency, but the wavelength is really short. These crests are really close together. Low frequency, longer wavelength. These crests are further apart. So high energy, low energy. The closer your waves are together, the higher the energy will be. So now let's talk about how light behaves as a particle. Okay, so we just said that light behaves as a wave, right? It moves exactly like a wave. But in 1900, this German physicist, Max Planck, okay, he began searching for an explanation because he found out that light also behaves as a particle. So the light also behaves as a particle, which he had to figure out what was going on. So he decided that it has wave-like characteristics, but it can also be a stream of tiny particles or bundles of energy called photons. So that's your blank for number 11. Okay, so we have light. It behaves as a wave, but it also behaves as particles, photons, discrete, small little pieces, but also a continuous wave. So this gives light a lot of unique qualities. One of the first ones about light is that light is connected to electrons. Okay? One of the reasons why it's called the electromagnetic radiation or the electromagnetic spectrum is because light has to deal with the electrons. Okay, so it's a form of energy. It acts like a wave and a particle, but light is caused by exciting electrons jumping energy levels and then returning to the original energy level. So we know that the low energy levels are closest to the nucleus and the higher electrons are further and further away. So we see different colors of light or wavelengths depending on how many energy levels the electrons move and the amount of energy they possess. So for example, helium down here is purple, right? But neon is this kind of orangey yellow pink. And argon is an even deeper purple, xenon is blue, and krypton is this kind of grayish silver. And it all depends based on how their electrons move. So let's talk about that. This is an electron on a low energy level. As the electron absorbs energy, it moves from its ground state, the original energy level, to an excited state, which is a higher energy level. So it absorbs energy and goes up an energy level. So the initial position of the electron is close to the nucleus, but then it absorbs energy and moves further away from the nucleus. Okay, so it goes from its ground state to its excited state, and it absorbs energy. But there's a problem with that, because electrons are unstable in that excited state. It's further away from the nucleus than it wants to be. And so what they do is they return to the ground state by releasing that energy, and it's released as a light photon. So the amount of energy, right, that's released is directly proportional to its wavelength. So the amount of energy determines the wavelength, which determines its color. So electrons start out on their ground state. They get excited when they absorb energy, and they could absorb energy through multiple different ways. Heat, electricity, the sunlight, all of these are different forms of energy that electrons could absorb. So let's talk about the final thing, the atomic emission spectrum. So an atomic emission spectrum is the fingerprint of an atom. Okay? It gives each element, when it absorbs energy, gives off a specific set of frequencies that are a series of colored lines, discrete lines. And what that means is we don't see a continuous wave of color. We see individual lines of color. And it's unique for each element, which means if we have the atomic emission spectrum of an unknown element, we can compare it to other ones. So if we look at this picture over here, we see that we have kind of an indigo line, 3 blue lines, and 2 red lines. Which element, beryllium, copper, manganese, strontium, or titanium, does that resemble? Yeah, that's right. It looks like strontium. We can see that these lines match up perfectly. So it allows me to determine which one. On your paper, you have some questions that ask you about your emission spectrum. Use that. Okay, I know that you can't see your individual colors because it printed off in black and white, but you can still match up the location of the lines and how many there are to your unknown A and B.